Welcome to the lecture series on the material testing in the course Basics of Mechanical Engineering 1. We have discussed about various testings in the previous lectures. We have talked about the tensile test, compression test, and bending test. This was discussed. This lecture will focus on the impact loads. Impact loads, that is the Charpy and Izod test would be discussed. The two impact load testing setups are there which are prevalent for testing the specimen for impact loading. Impact testing. What is impact testing? Impact testing is a method used to assess the behavior of materials when subject to a sudden loading conditions such as impact or shock. This test measures the ability of a material to absorb energy under dynamic loading, providing insights into its toughness and resistance to fracture. Impact testing is crucial for evaluating the performance and reliability of materials in applications where sudden impacts or dynamic loads are common. So, this is a specific impact testing machine. We have a striking edge. So, here energy is stored in the form of potential energy. This potential energy is converted into the kinetic energy here. We will watch that in the video. There is a scale that shows loss of energy. This loss of energy is then put proportional to the strength this specimen had. So, this is a test piece that is held here because this test speed is hit at the end. So, it is our Izod test. So, there are differences between Izod and Charpy. I will give you the differences. So, this is axis of rotation, this is friction pointer, the supports are there so that the specimen does not slip. The test piece is there, main machine framework is here. So, this is a setup that is there for the Charpy test, where the notch to get the specimen broken or to get the specimen bent is at the center. Why impact testing is important? First is performance evaluation. This quantifies a material's ability to absorb energy and resist fracture under dynamic conditions, guiding its suitability for real world use. Wherever or whenever impact is there or dynamic loading is there, impact could come. So, this is designed for the real world use for its performance under these conditions. Then is design optimization. It helps in selecting materials and improving designs to enhance impact resistance, leading to more durable products. Quality control. It helps in verifying the material consistency and reliability during manufacturing, ensuring adherence to the required standards. Let us go through the procedure. First is specimen preparation. Again, based upon the ASTM or ISO standards, the specimen are prepared here. Surface preparation, specimen surface roughness has to be smooth and free from defects so that there is no variability. There are some specimens which are shown here which have gone through the impact testing apparatus. We have impact tester, use a dedicated impact testing machine designed to deliver controlled impact forces to the specimen. Specimen mounting, securely mount the specimen in the testing apparatus to ensure it remains stable during the impact. So, that is why we put it on a holding device here. So, this is a striker comes in this direction. When it is a center, always remember again it is Charpy test, and there is a notch. There could be kinds of notches. I will show you the kinds of notches. It could be V notch, it could be U notch, it could be saw cut notch, and there are supports so that the specimen is bearing the force completely and it is not transferred to any other part of the machine. And measurement and calibration. Calibrate the impact tester according to the manufacturer's guidelines to ensure accurate and consistent results. Measurement instruments use sensors or transducers to measure impact force and deformation of the specimen during the testing. Then we conduct the test apply impact load, that is when the load is held here, it is carrying a potential energy, it is released, that is released pendulum or striker from the specified height or velocity to strike the specimen. Here kinetic energy is maximum kinetic energy. So, when we record the data, capture the impact force and deformation parameters such as energy absorbed, displacement and fracture type during the test. The specimen is held in the specimen holder vise here, and this vise is here, this vise is here, and then we conduct the test. Then we go for the data analysis, that is we evaluate the results, analyze the recorded data to determine the material's behavior under impact, including its toughness, energy absorption capacity and resistance to fracture. Then we compare the standards, that is we compare the test results with established standards to assess compliance and suitability for intended applications. To talk about the equipment could be pendulum type or drop weight type, that is impact testing machine. Pendulum type equipment is very commonly used, where a pendulum swings down to strike the specimen, or a falling weight could also be used to generate the impact. So, the two kinds of equipment are there, but pendulum type equipment is smaller in size and is generally used for the impact testing. Specimen holder fixtures hold the specimen securely in place during the impact testing. This ensures it is aligned correctly with the striking mechanism. Then comes the DAQ, data acquisition system, or we call it as DAQ, data acquisition, sensors and transducers. The setup that I will show you would be having a manual dial indicator, but there are nowadays sensors and transducers that measure the force and just display it on a digital display board. It measures the impact force, deformation and other parameters. Computer interface helps to collect and process the data to generate impact test and curves. Only the point is it has to be calibrated, and calibration has to be timely and periodically. That is, maybe each 3 years it has to be calibrated, each year it has to be calibrated, or after a number of tests, maybe after 100 tests, 1000 tests, there are specifications with the machines which are given, it has to be calibrated accordingly. Then comes safety precautions. Safety enclosures shield operators from potential debris or fragments during impact testing. The PPE, that is personal protective equipment, ensures that operators are safeguarded against any hazards. Now, I will show you a video where the impact test, that is a Charpy impact test, is conducted on two test specimens. First test specimen is strain aged plain carbon steel S235, and second specimen is the normalized steel. You will see the strength that is for the normalized steel is very high, that is the energy that will be absorbed for the normalized steel would be heavy, because normalized steel is heat treated and it has gained strength accordingly. So, let us go through this video and I will come to the simulation part of the impact test.
The standardized Charpy impact test has been designed to measure the toughness of materials under impact loading and multi-axial stress state. A pendulum impact testing machine is used to do so. The pendulum on the machine has a heavy weight at the end. This is lifted into the starting position in step 1. Then the tester checks whether the testing machine has been adjusted accurately. In order to do this, he turns the drag indicator downwards and releases the pendulum without a test specimen. The drag indicator stops at position 0. This proves that the pendulum has the correct starting position and that the friction is correctly compensated. The machine is ready for the tests. First test, strain-aged plain carbon steel S235. This is our test specimen. It has been machined to standardized size and shape with the characteristic V-shaped notch. The tester places the specimen on a support in the lower part of the machine and adjusts its position with a centering device. Next, he turns the drag indicator downwards again and checks that everything is prepared correctly. Perfect, the test can begin. The pendulum is released, it swings downwards and hits the specimen with its rounded hammer peen. The specimen absorbs part of the pendulum's energy, so the pendulum doesn't reach the full height on the other side. The amount of energy that has been absorbed by the specimen can now be read off at the position of the drag indicator. It only amounts to 13 joules in this test. Here is the main principle of the measurement. In its starting position, the pendulum only has potential energy. It is given by mass of the hammer m times gravitational acceleration g times starting height capital H. After the pendulum has been released, the hammer moves downwards, hits the specimen and then only swings to height small h. Exactly at the first reversal point, the pendulum again only has potential energy, which is m times g times small h. The energy that has been absorbed by the specimen is called notch impact energy, kV. It corresponds to the difference between the two potential energies. The first specimen only shows very little plastic deformation. A mostly flat, slightly glittering fracture surface has been formed. This is another important indication that this kind of steel is only able to absorb small amounts of notch impact energy. It shows mainly brittle behavior due to the strain aging effect. Second test. The second specimen has been made from normalized steel S235. It is also placed on the support and centered. The tester turns the drag indicator to its starting position, rechecks all safety measures and releases the pendulum. This time the impact sounds much deeper and richer. An impressive energy of 182 joules has been absorbed by the specimen. Here the specimen did not break into two pieces. Instead it was pushed through the counter bearings under heavy plastic deformation. In comparison with the strain-aged steel, the normalized steel absorbs much more notch impact energy and behaves in a very tough manner. The Charpy impact test is not only carried out at room temperature. Materials with body-centered cubic crystal structure, such as plain carbon steels, show a characteristic S-shaped curve of the impact energy versus temperature. In the so-called upper shelf region, the material absorbs a lot of energy and behaves in a tough manner. At low temperatures, in the lower shelf region, only a small amount of impact energy is absorbed and brittle fractures occur. Metallic materials with a face-centered cubic crystal structure, on the other hand, do not experience a ductile to brittle transition. These materials retain their ductile behavior towards low temperatures and are therefore well suited for low temperature applications.
I think this video made it very clear that there was a potential energy that converted into kinetic energy and how the specimen is broken or the specimen is bent depending upon the energy that is absorbed here. Each time the specimen behaves a little different. That is why we go through 3 trials at least when we try to conduct a test. This was the Charpy impact test. Izod impact test is also there when the specimen is broken at the end. So let us go through the simulation part of it. So this is the virtual laboratory experimental setup for the Charpy impact test. The aim is to find the impact resistance of mild steel. I have picked mild steel specimen here. The theory part is given here where the machine setup is given. Here fracture energy is given. So this is the setup of the specimen. There are anvil here on which the specimen is mounted. We need to make sure that the notch is facing in the opposite direction to the striker. If striker is coming from this direction, notch is in the opposite direction. Notch should be in this direction. So here the specimen will strike at the plane end or plane surface of the specimen. So now test supports are there, width of the specimens are all given here. The diagram is mentioning it very clearly. When I will show you the specimen getting broken, or when you watched in the video specimen was broken, you saw there was brittle setup here, or brittle fracture area was there, that is shown white here, and there was ductile fracture area that is shown grey here. Also you can see the A and B or width of the specimen. When we try to look at the cross section of the breakage, so this is brittle fracture and ductile fracture, the transition between them, the impact energy, this is the plot that we have gotten, and the notch is in a way that it is 10 mm and lateral contraction is just like this. So we can calculate the shear area, and this is the notch section. These are the nominal dimensions of the notch. Length is 55 mm, width is 10 mm, thickness is 10 mm, and we have also been given the machining tolerances here, that is these are permitted here. Then we have kind of the notch shapes, that is V shaped notch is there, then we have U shaped notch, we have saw cut notch in which there is a circle of 2 millimeter, that is a hole of 2 millimeter, then it is saw cut. The different notch types are there to conduct the test. So these all are the standards developed by different standard organizations such as ASTM or certain ISO standards are there. So let us go through the evaluation questions first. In Charpy impact test, the specimen is kept as, so it is simply kept there, so that is why we can select here, it is simply kept as a simply supported beam. It is not overhung, it is not cantilever, it is not fixed at any end, it is just kept there. Then tensile and bending stress also gives impact resisting qualities of material. No, tensile and bending stress does not give the impact resisting properties. Match the following in the Charpy test. Angle at the tip of the hammer, that is one angle at the tip of the hammer is 30 degrees, the angle has to be matched, one is D. So there are two options A and D which are showing, one is D. Then radius of curvature at the supports, radius of curvature at the support is 10 millimeters. So that means 1D, 2E, again A and B could be the answer. Third is length of the specimen, that is for the Charpy impact test is 55 millimeters. So that is 3 is matched with B. So answer should be A, in which angle of the tip of the hammer is 30 degrees, the radius of the curvature at the support is 10 millimeters, the length of the specimen is 55 millimeter, the width and thickness of specimen are 10 millimeters each, that is square cross section, and distance of the center of notch from end of test piece is 27.5 millimeters, which is half of the length of the specimen. This is 55 by 2. So this answer is marked. Next question, stress induced in a body due to suddenly applied load compared to when it is applied gradually is 2 times. When suddenly applied load is there, stress that is induced is double. So that we have also discussed in one of the numerical questions in the previous lectures. Then next question and the last one is quantitative result of the impact test. The energy needed to fracture a material can be used to measure the toughness of the material, and when we are measuring the toughness, we are also measuring the yield strength. Let us submit it 5 out of 5. Please get 5 out of 5, keep resubmitting, understand it completely. This is what is the purpose of having a self evaluation or pre-test evaluation before conducting a simulation. Let us go through the simulation and we will have 3 trials. This is the Charpy impact test setup, and this is using sensors and transducers where the reading would be displayed here. I have to just release the load here. I will just rotate this lever and the load is released here in the pendulum, and there is a loss of energy due to friction, that is 1 joule. So that is, this is the calibration of the machine before testing. 1 joule of energy is lost when no specimen is there at all. Now let us try to get our specimen. These are the dimensions of the specimen that we have discussed. Length is 55 millimeter, width and thickness is 10 millimeter each. The depth below the notch is 8 millimeters, and distance, that is the center of the specimen, midpoint is 25.5 millimeter. That is the distance of center of notch from ends of the test piece. So this is a specimen that is with us, and we can select either cast iron or mild steel and try to test it. Let me select mild steel only. This is mild steel. Length is given here, breadth is given here, depth is given here, depth of notch is also given here, and this is V type notch. So this is my specimen holding vise here, and on this vise I will drag the specimen and just put it here just as a simply supported beam. Let us go for the trial 1. Now I have to release the load. Specimen is broken. Specimen is broken. It will show you us the energy that is absorbed here. The test piece is not broken here. So that is, test piece was not broken by the striking energy of the testing machine. So the impact value obtained is indefinite. Once we have obtained any value, whatever it could be, because the specimen is not broken, the test is invalid here. That is, loss of energy is 1 joule. The total loss of energy during transit of hammer is indefinite. The energy for the failure specimen is ET minus EF. That is total energy minus the loss of energy, that is indefinite. Let us go through the second trial, mild steel specimen again. The second trial again, I will put the specimen here and conduct my test. I have to release the lever. Yes, now the specimen is broken. Specimen is broken and it is showing that the energy that is loss is 43 joules. That is total loss of energy during transit of hammer. ET is equal to 43 joules. The energy of failure of specimen, that is ET minus EF. EF was 1 joule. That is 43 minus 1 is 42 joules. Let us conduct the third trial, or in the second trial, let us try to first see the calculations. How do we get 42 joules? So this is the second trial result. Third trial, again I will mount the specimen. Mounting is just keeping the specimen so that it is exactly at the center. Then we conduct a test in the similar fashion. Again the specimen is broken. When the specimen is broken and energy that is lost here is 43 joules. Again the same energy has come. It could be different. It could be, maybe if it is 43, it could be 44, it could be 42, but again we have gotten the same values and we will find the final values. That is, for the first trial there was indefinite because the specimen did not break. In the second and the third trial, both of them have gotten the loss of energy during transit of hammer as 43 joules. This energy minus the energy loss due to friction, that is 1 joule, is 42 joules each. So average energy of failure of specimen is 42 joules. This is the result of the Charpy impact test. Let me also go through the IZERD test here. This is the IZERD impact test, where the aim is to find the impact resistance of mild steel and cast iron. Theory, only the difference between the IZERD and the Charpy test is, in IZERD test we break the specimen at the end. So high stress concentration factor at the tip of the notch, area of local yielding of material reducing the stress concentration effect. So there are certain interfaces of the notch given here to show the weak interface, and these all could be studied. So this is our experimental setup. It is very similar to what we had in the Charpy impact, only we see the scale is here and lever arm is there and hammer is here, and the specimen is held in this way. Here the striking height is here, where the striker would hit or strike the workpiece. The radius of curvature of the striking edge is there, and direction of impact is here, and the notch direction is towards the striker. This is also one of the differences. The notch direction in the Charpy test was opposite to the striker. Here the notch is towards the striker. So test specimen dimensions are here 75 millimeters, and we have at 22 millimeters from the hammer striking point, the notch center point. So this is 45 degrees V notch. Let us try to go through the self evaluation questions. The IZERD impact test, angle at which pendulum is placed from the ground is 90 degrees. How the test piece is supported here? Here we have a vertical cantilever and it is supported accordingly. Which property of metal is used to check in this test? Ductility, toughness, brittleness, malleability. Definitely we are checking the toughness here. The initial energy of hammer is 164 joules. This was written in the theory. I am just marking the answer. According to the IS course dimensions, the length of the test piece is, length of the test piece we have seen was 75 millimeters. What is the depth of the notch of IZERD test specimen? The depth of the notch was 2 millimeter only. The toughness value of material A and material B are 60 joules and 5 joules respectively. Which of the following statement is most suitable? The toughness value of material A is quite higher than material B. Let us see the statements. Material A is harder than material B. Material B is more brittle than material A. Material A is more tougher than material B. The material B is more ductile than material A. Here, because we have gotten toughness value, we can talk about the brittleness here. So here I will put it as material B is more brittle than material A. Let me submit. I got 7 out of 7. Let us go to the simulation part here. This is our apparatus and different components of operators were shown in the theory. Let me go to the test step 1. Select the ISO test specimen. I will select mild steel once again, and length of the specimen is 75, breadth is 9.3, depth is 9.4, depth of the notch, that is D, is 3.34 millimeters. The loss of energy we will first review. Test for the friction loss is conducted by adjusting the pointer to 164 joules. This pointer is set at 164 joules. Then the pendulum is released by operating the lever without keeping the specimen. So, without the specimen, let us see what is the loss of energy. 2 joules of energy is lost just due to friction. Now, let us try to start conducting the experiment. We have again the specimen held here in the vertical form, that is 90 degree to the ground, and radius of curvature of striking edge, test piece, everything is given here as we saw in the theory. Let us now conduct the experiment. I will release the pendulum and it is broken. Total loss of energy due to transit of hammer is 44 joules. So, energy for failure of specimen is total loss of energy minus loss of energy due to friction, that is ET minus EF, that is 44 minus 2, that is 42 joules, and initial energy of hammer was 164 joules. So, here energy of failure is given. Second trial again for the same specimen size. I will release the hammer, specimen is held here. Test piece was not broken by the striking energy of the testing machine. So, impact value obtained is indefinite. So, this test is a fail. Let us go to the third trial now. Here length of specimen is given, breadth is given, depth is given, depth of the notch is also given. Let us try to test this. Specimen is held, the notch is in the direction of the striker. It strikes, it is broken now, and the energy that is obtained here is 56 joules. 56 joules implies the energy for failure of specimen would be 56 minus 2 would be 54 joules. So, that energy we have obtained. For the first trial, the total energy lost was 44 joules, and for the second it was indefinite, for the third it was 56 joules. Accordingly, we have gotten the energy for the failure of the specimen as 42 indefinite and 54 for the trials 1, 2 and 3 respectively. So, average energy of failure is average of these two values, that is 42 plus 54 by 2, that is 48 joules. This is how we conduct the impact test. Impact test also has multiple applications. To showcase a few of those, I have just picked applications in automobile industry. So, it ensures safety, it evaluates how vehicle component withstand crash scenarios. When the crash is there are certain points when the locking is there, these points are there. In the scenario of the crash, what impact energy is required at safety belt points, at side impact. These are the points or the areas in a vehicle, in a car, where impact could be borne. That is front crumble zone, the ABS system, the side impact bar, the safety belts, rear crumble zone, passenger safety cell, safety glass, airbags, all of them bear impact in the case of accidents, in the case of sudden brakings or so. So, guides material selection, determines optimal materials for crash worthiness, drives design innovation, that it helps to improve the vehicle safety and standards and regulatory compliances. So, this was impact testing. I will also discuss hardness test and some other test in the coming lectures. We will continue the material testing series. Thank you.